Action movies are renowned for defying the laws of physics, whether that be in scenes with gunshots, brutal fistfights, or my favorite, car scenes. And while this is something they all have in common, none does it more than the John Wick series, specifically in John Wick 3 Parabellum. At the end of the movie, John Wick is forced to jump off the edge of the Continental in order to flee from Winston, one of his former allies and someone who betrays him, hitting the fire escape on the opposite alleyway and going into a series of free falls. So let's use kinematics, forces, and kinetic energy to find how much energy Wick hits the ground with, and if it's actually possible for him to survive.
What are we going to do about John Wick?
Oh, he has to die. Sorry, Jonathan. Don't see any other way.
Our first step is to measure the dimensions of the set used during the filming of the actual stunt, so we can refer to Parabellum's production visual effects supervisor Rob Netterhist in the video that he has posted on the left. By measuring the amount of centimeters that each section takes up on the screen and a ratio of the total height, which is 27.12 centimeters, and the real life height of 40 feet, we can find the actual height in real life of each section that John Wick falls. Section's height divided by 40 feet and the conversion factors from meters to feet, we get the real height of each section in meters. And then we can set up a free body diagram, in which by using the side lengths we find that the angle is 47.66 degrees. And then we can use this angle to find the individual components and the individual amount of force that gravity is having on John Wick as he goes down the slope. More specifically, we can set up the equation sine 47.66 equals the force of gravity x divided by the force of gravity as a whole, and cosine 47.66 equals the force of gravity y divided by force of gravity as a whole, in which we find acceleration in x to be 7.24 meters a second squared and acceleration in the y to be 6.60 meters a second squared. And then we can use kinematics in order to find the velocity at the edge of the slope. And by plugging into the equation, velocity final squared equals velocity initial squared plus 2ax minus x initial, we find that the velocity final x is 6.9 and the velocity final y is negative 7.57 meters a second. And now, we can set up our free body diagrams and kinematics for both freefall 1 and 2, using the same equation mentioned earlier, and the only force existent on John Wick is gravity itself. And then, we see that the final velocity after hitting the fire escape is negative 9.44 meters a second, and during his second freefall, goes to negative 12.4 meters a second. Since we never learned how to calculate the x velocity, we can assume that its magnitude stays the same, at 6.9 meters a second. Now, we can use the conservation of momentum and the overall rules we've learned about momentum to see how his collision with the AC unit affects his velocity, using the initial velocities that we calculated before of negative 6.9 and negative 12.4. The conservation of momentum tells us that mass times velocity in one object plus mass times velocity in another object is going to be equal to the same masses and velocities in the final calculation. And by finding the velocity of the AC unit, which is negative 2.168, and the mass of John Wick to be 87.1 kilograms, we can use that and plug it into the calculation below, in which we find that the final velocity of John Wick as a result of this loss of momentum is negative 10.66 meters a second. Then, after a short free fall, he goes to negative 12.41 meters a second. So, that means that after hitting the ground, he still has this velocity. And then, if we want to calculate how much energy he actually strikes the ground with, we can use the equation of 1/2 mv squared, setting up a triangle in both his collision with the fire escape and his final collision of hitting the ground, in which we find the hypotenuse to be 11.69 with his collision in the fire escape and 14.20 in his collision with the ground. And then, by plugging that into your initial equation of 1/2 mv squared, we find that with his collision with the fire escape, that's about 6,000 joules. And in his final collision with the ground, it's almost 9,000. Just to put that in perspective, his ground collision is about 2 to 3 times the kinetic energy of a high velocity bullet or being hit with a soccer ball 30 times. So that makes it clear that in reality, John Wick would not have survived.